Yeah, comes on everyone. Let's start off. Great. So this is the last thing that we did. Great. So last class, right, we have dealt with this force between the charges, right, and the force when you keep the charges in a medium and everything. Great. Now the issue is, so whenever the scientists, right, start seeing any phenomena or anything, right, we want an explanation. Like, for example, the biggest problem people had was this: if you keep a charge Q1 here, and if you put a charge Q2 here, right? And you're saying there's a force between them because of repulsion or whatever, right? So the question is this: how does this Q1 know that this Q2 exists here? You're getting it? How does one charge know that there's a second charge somewhere else? How do they interact with each other? Like, how do they know, boss, okay, because there's a Q2 here, you should get repelled now? You're getting it? So physically, we have observed this phenomena, they're repelled, but how do they actually interact with each other? You're getting it? It's like, for example, see, you're standing there and suddenly you turn back. Maybe someone is shouting and that's why you're turning back, isn't it? So something must have happened. So this Q1 must have done something so that this Q2 will get repelled. So people wanted a theory to explain this, right? So they made up a theory, right? We call this thing field theory. So this is mostly a hypothetical thing, but yeah, it could explain all the things that we have been observing so far. So this thing can also explain gravitation. It can also explain magnetic field and electrostatic field. So what field theory says is a body modifies its surrounding by creating field lines. And when another body enters this region, they interact. So if you see, so the concept of force is real, but this is a theoretical abstract, this is theoretical thing which we constructed in order, for to explain what is happening. If I have to give an analogy, think of like this. Ever seen a spider ka web? You know how spiders hunt? The spider makes a web. I'm just giving an random example. And then what the spider does, it just sits in the center. So when some mosquito or something comes here and hits this, the vibrations travel through this string and reaches the spider. And that is how the spider knows, okay, now I have to go to this side and catch the insect or whatever. So maybe they got inspired by this or something. They said this is how charges also interact. So when you have a charge in a region, this is going to, emit field lines throughout the space. So if you take a plus Q charge and if you take a minus Q charge, so this plus Q charge will emit field lines away from this thing. Again, completely a theoretical construct. So positive charges will emit field lines and negative charge will absorb field lines, or you can see the field lines end at a negative charge. So someone came up with a theory like this. Getting it? So now when you put a charge somewhere in this region, so they are going to disturb the field lines in that region, and this plus Q will come to know, okay, there is a charge here, and that's how to interact. You getting this? Like I'm saying, when something happens, you always want a theory to explain. So people created a theory, and so far it is working out. Meaning, if you think about it, look at your chemistry. We wanted to study how electrons and how protons are inside a nucleus, inside an atom. How did we start the theory with? We started with the J.J. Thomson model, isn't it? Pudding model. So this guy said the nucleus is like a watermelon, positive charge is distributed, and electrons are seated like seeds. Then Rutherford came and did an experiment, and he said, "Boss, this is not going to work out." The Rutherford gold foil experiment, he said, the charge must be located at one place, positive, and electrons are going around in circles. Then Bohr came and said, "No, no, boss, this planetary model won't work because the electrons will collapse. So there are some specific orbits where you can go." Then Sommerfeld came and said, "Boss, it is not circular. These are actually elliptical orbits." Then Schrodinger came and said, "Boss, there are no orbits only. It is just a wave probability." You can see how the theory. So the thing is, as long as the theory is able to explain the phenomena, it is okay. The day it can't explain, you change the theory. So this field theory is also able to explain so far. So we are okay with this. But if it is not, we're going to change it. So let's see the properties of this field lines. First one, the positive charge emits field lines. And at field line, at negative charges, field lines converge. Now, how many lines we have to draw? So the number of lines that you draw is proportional to the charge. The field lines will come from infinity.
So they don't need a source to.
They need a source.
Okay.
Again, like I'm saying now, you're thinking field lines are some kind of quantities. So first of all, if you ask that way, why the hell should the positives emit field lines? Where are you getting the field lines from? Is it storing field lines and it's suddenly blasting like a bomb or something? No, right? So after some time, shouldn't the field lines get exhausted? So it's not like that. What you're thinking, it is not some kind of quantity of water or something where it is just pushing out. Hi, you can give an analogy like that. It is like a water gushing out from a hole. And negative charge, you can assume like ever seen kitchen ka sink when it is get clogged and you remove the clog and the water is just getting absorbed inside. A negative charge kind of behaves like that. Yeah, yeah. So yeah. So the number of lines is proportional to the charge. For example, exam they would ask you something of this sort. Let's say we have a charge Q1, we have a charge Q2. So they'll give a picture like this and they'll ask you find Q1 by Q2. What is the answer? The picture is not up to scale. So just now I wrote the statement, the number of field lines is proportional to the charge. So if you count the lines, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and this thing has 15 lines. This thing is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So Q1 will be plus 15 and Q2 will be minus 10. Signs are also important. If you see Q1 cell lines are coming out and Q2 cell lines are going inside. So the charges will be in the ratio of 3 is to minus 2. Is that making sense? So lines going in, lines going out also will make, or make a difference. And how do you know how many lines to draw? Now, this is completely arbitrary. Did you ever see a map? In school, you must have drawn that India ka map, right? A4 sheet mein. And on top of it, if you ever observe, they'll be writing a small thing like this. 1 centimeter is 200 kilometers. Ever seen something of that sort? Basically, that's your scaling factor. So every 1 centimeter on the map is equal to 200 kilometers in the real life. So something similar, if you have a small paper, I'll draw less field lines. If you have a big paper, I'll draw more field lines. So for example, if you say, so the number of lines, right, from charge is arbitrary. So there's no fixed number that is like you have to draw this many lines. So we can choose whatever we want. That is, we can choose, let's say you decided to draw 1,000 lines for 1 coulomb charge. Now, once you say this, then you're fixed. Then you have to draw 2,000 lines for 2 coulomb charge. It becomes proportional. If you have a big paper, then you can draw 1 lakh lines for 1 coulomb charge. Getting it? So it's all that you know is that ratio. You can decide any quantity, but you have to fix up that quantity for everything. Next thing. So using this thing, we can actually find even more. Any doubts on this page? Daksha, Parth, Vignajit, clear? Surya, Nikhil. Now tell me one thing. If I take a conductor, if I put a plus Q charge here, we have seen this thing in induction last class. You will induce a negative charge here, minus Q, and this will become positive on the other side, plus Q. Can you tell me which one is greater, capital Q or small q? So this Q small q is your induced charge. This capital Q is your source charge. Now the question is this: if you put a charge in front of a conductor, it induces charges minus small q and plus small q. Whose magnitude is more? So the options will be like this: Q is greater than small q, Q is less than small q, Q is equal to Q. The values will depend on the distance between the charges. Something like that. They'll give 4 options. What can you say about this? Greater, equal. Okay. Why do you guys think it is greater? Any solid proof? No. See, you need to understand. If this was the final JEE exam, will you have guts to mark that answer? And what is the reason for that? Equal. Okay. Why do you think Kanshit is equal? Any logic?
Because capital Q cannot like give small q and small q. It can give like only its same kind of charge.
No. See, this
That's
whole
what I
body was
thought.
neutral. Whole body was neutral, na? See, as long as these two are equal and opposite, my problem is solved, isn't it? Bodies are neutral.
But we cannot remove like small q for it to be induced. We can't just remove small q from capital Q, right?
No. This charge to move nahi kar rahe na. You're not
Ah,
removing anything from here.
right. But I thought of something on
You
that.
thought of
It's hard to
something.
explain.
Nah. Okay. Then, I don't know, Niharika, want to say why you think Q is greater than small q? Any reason? Or just a whatever it is? What do you think? Couldn't think of? Have something but can't put it in words. Okay, happens. Listen, the thing is, if I try to draw the field lines, no, it's a good question actually. This is a pretty good one. Even at an advanced level, it's a good one. If you draw the field lines, and they will be perpendicular. We will see why in later on. But for now, take it from me. The lines will start at the positive and end at the negative. This being positive charge, you will also have lines going else in every direction. Did you notice something? Every line that minus small q gets it will get it from plus q, because plus q is creating the minus q, isn't it? So because of plus q, you are getting a minus q, the induced charges. So every line the minus q gets it will get it from capital Q. But this plus q also has some lines going in some other directions. So in terms of lines, who has more lines, small q or capital Q? Capital Q, isn't it? So the magnitude of capital Q must be greater than small q. You're getting the argument? Again, we are using this statement here. The number of lines is proportional to the charge. If you're going to put a plus q charge here and if you put a minus q charge here, some lines from plus q will go to minus q. Agreed? But some lines from plus q will also go on the left hand side. That means overall, in terms of number of lines, the capital Q will have more lines than the small q. Is that making sense? Okay. So, oh, that's a different thing, Vihan. You can't have lines coming from here to here. That is not possible. We will see that later on. We have that has to do something with something called potential. So look at this thing. So all field lines of minus q start from plus q, right? Because the plus q is responsible for creating minus q. What do you mean by creating a responsible? Think about it. First of all, why did the charge even move in the first place? This thing started attracting the electrons now. So these field lines, when they're passing through the conductor, these electrons got attracted towards these lines and they came and got stuck on the surface, isn't it? So who created this minus q? The plus q field lines. Is that making sense? What I'm saying is plus q also has some lines on the left hand side. So all the right hand side lines maybe will get absorbed by the conductor, but the left hand lines are still there. That means overall, in terms of number of lines, the plus q will have more than the small q. Is that making sense? No? Is that clear? Right? And we can clearly see here number of lines of capital Q is greater than number of lines of small q. Therefore, you can be sure q is greater than q. Now, what Vihan asked, if you have negative and if you have positive, you cannot have a line like this. This is not possible. You cannot have lines like this thing. Because tell me again, why did you get plus q in the first place? Because this electron went away here, you got a plus q now. So minus q and plus q are not created due to each other. But there is another reasoning also, but we will need more about that. We will talk about that in potential. Right? So I'll just write down the reason for now, and later on, I think you'll understand. Because later, when you refer the notes, you will think what it is. In the direction of the field, potential changes. And a conductor is equipotential. Means the entire conductor has same potential everywhere. So if you have a field line going from one point to another point, then you're saying that there is a potential difference. So there is an argument like that. I will teach you that when it comes to potential. I will refer this again then. So for now, keep it in mind. We'll prove this thing more later on. So there, they can ask you a question like this also. The third point. Let me write on the next page. But is this thing clear, everyone? Why plus Q will have more than minus Q? So the electric field lines the electric field is tangential to the field lines. That means if you have an electric field line, so at every point, this will be the direction of field. Getting So if you ask me exactly what is this field, you can think of like this, field is nothing but this is a direction of force. If you put a charge on this, it will get pushed in that direction. We will define what is field exactly. And then suppose if you have a lot of field lines like this, so here you have a bunch of field lines. You also have the same number of lines, but they're a bigger area. So number of field lines per unit area gives you the magnitude of field. So if you have more lines in a smaller area, you'll get more field magnitude. What do you mean by that? Think of like this. If you have a lane, a big lane, and if you have a small lane, and if 10 people are going through this, you tell me in which case there'll be more pressure or more force. Isn't it more difficult for 10 people to pass through a smaller lane? So they will push more harder, right? So think of like that. So when you more lines constructed in a smaller region, right, they will apply more field or more pressure there. So the field at point A is greater than field at point B. So there's a number of lines per unit area is proportional to the magnitude. Now here I have a doubt. Listen to this question. I take a charged particle, put it on a field line. All right. I take a particle and put it on a streamline. Remember what is a streamline? So I have two options. I have a field line, I have a streamline. If you put a charge on a field line and if you put a particle on a streamline, what will happen in both the cases? So for example, you think of like this. So let's say we have a bunch of field lines. These are streamlines. You kept a particle here. You kept a particle here. Let's say charge Q. What happens? Let's go back to the definition of a streamline. What is the definition of a streamline? If anyone remembers how we defined a streamline, here, look at this thing. A streamline is the path of the particles move. Is that making sense? So if you put a particle on a streamline, what will happen? It will follow the streamline, isn't it? Because that is how we defined it. It is the path of the particle. So if you put a streamline here, this guy will follow the path. So it will go along the line. So streamlines are path of the particles. Right? Particle moves along streamline. What about a field line? Remember, I said field line is the direction of force. So the moment you put the charge here, you will get a force in this direction. So it will get pushed away in that direction. So it will go along this line to this point. Then it will get pushed away like this, right? But by then it also must have acquired some velocity. So now it would go like this. So once it reaches here, it will get pushed away like this. So this particle is going in a pretty weird way. You're getting it? So every time you touch a streamline, you'll get pushed away tangentially. So you won't follow the streamline, right? So these are the directions of force. So you won't follow the field lines. Not necessary. So particle is pushed away tangentially. You're getting how it looks? Again, the left one I just drawed it approximately, but yeah. So it'll push this thing. Whenever you touch the field line, it'll again push tangentially. When you go to the next line, again you push tangentially. So you won't follow the streamline. You will go in some weird path. Is this clear, everyone? So that is the difference between a field line and a streamline. Both are lines only, right? But yeah, they have a different nature. If you remember, उसमें भी number of streamlines per unit area gives you the flow rate. If you have more streamlines in a small area, mean the volume of liquid flowing was more. So in terms of that, the field lines and this thing will look same. So they do have some similarities, but yeah, the whole definition is different. We keep saying a theoretical question. They ask like this only. Is this clear? Next one. Two field lines never intersect. Why? Because just now we defined the direction of the field is tangential. And if you have two field lines intersecting, then you have two tangents at the point of intersection. That means you're saying there are two directions of field. You can't be looking at right and left at the same time. So at point of intersection, there will be two directions of field. Not possible. But let's say you insist Naser field lines are definitely intersecting. Then what does it mean? How is that possible? First of all, they'll not intersect. But if you come and insist, no, they are going to intersect, then what does it mean? What do you guys think? They are not supposed to intersect, but if they intersect, what does that mean? Again, I'm telling you, right? Field lines are not some kind of real things. They don't exist. They don't fight with each other. Again, understand the meaning of it. What is the problem actually you have if they intersect? Electric field have two directions. That is a problem. No, that is the reason why we said it is not right. But you are saying no, no, they're intersecting. So let me ask you like this: do you have a number which is both positive and negative at the same time? You have a number which is both positive and negative at the same time. Zero, right? So if at all you insist they intersect, then there's only one possibility. The field must be zero there. Because a zero vector will have any direction, isn't it? A null vector We can take any direction. A zero vector need not have a fixed direction. Then it must be a null vector or a zero field. So the problem of two directions will get solved. Clear? So technically in a diagram, you'll never draw actually. You're getting it. So that point will actually vanish. So the line, it would be like this, meaning there'll be no lines only there. So first of all, we won't draw, but if you someone insists it they're intersecting, that's what it means. That's a null point. Clear with this? Fifth point. Field lines propagate with the speed of light. So if you put one charge on Earth and one charge on Pluto, the charge on the Pluto suddenly won't know, okay, there's a charge on Earth. It takes time. There is a delay. In Einstein's theory of relativity, we say like, no information can travel faster than speed of light. So if you have two charges and if they interact with a zero time, you can actually send information, isn't it? I can make this charge go positive, neutral, positive, neutral. The other charge will get repel, not repel, repel, not repel. You created a Morse code, on and off. Getting it? So you can't send any information or anything faster than the speed of light. So this thing, right? When Newton was proposing his gravitation theory, right, he know there is something wrong with this theory, right? Because Newton proposed that the gravitation field travels with the infinite speed. Means the moment you put a mass here, so for example, in this case, if you put a charge 1 coulomb here, if you put another charge 2 coulombs here at a distance of 6 into 10 power 8 kilometers, it takes light 2 seconds to go from here to here. So after putting this charge, it takes 2 seconds for this charge to get repelled. So there is a delay in interaction. They won't repel immediately the moment you bring the charges. But in day to day, the distances are so small you can neglect it. But when the distances are far, it does affect. So, for example, think about this thing. Let's say if sun suddenly vanishes, gone, completely gone, what do you think will happen to the Earth? Earth is going around the sun due to gravity. Whatever, blah blah blah. Sun suddenly vanished. What will happen to the Earth? Hmm. Right up, So, what do you guys think? Right, Nikhil. Thing is, few years nahi hai. It takes Earth, it takes light around 500 seconds to go from sun to Earth. That means the light which you're seeing outside right now was actually emitted 500 seconds before. So when you see the sun setting, the sun has actually set 500 seconds before. When you see the sun rising, the sun has already gone up 500 seconds before. So every time you see in the night sky, the stars which you're looking at, those stars are not there. The nearest star system you have is Alpha Centauri, 4.2 light years. Means it takes light 4.2 years to come from there to here. So every time you see that star in the sky, that was the position of the star 4 years back. The star is not there anymore. So every time you see in the night sky, all those stars which you're seeing, none of them are there. They all have moved on. What you're seeing is the past. You're getting it? So that means if suppose aliens, right? Let's say who are at a distance of 1,000 light years. So if these aliens are looking at Earth through a telescope, you know what they will see right now? They'll be looking at the year 1025. They'll be seeing, we are fighting on horses. People are still doing agriculture on, small things. We are just tribals and everything. So what they'll be looking at into the past. So if you actually have a planet which is super far, 65 million light years, they will see dinosaurs roaming on Earth. Getting it? So that's what happens. And that is one of the problem we are facing also. If you make, probes and everything and you send them into the space, I think I told you this thing. Let's say if you're on Earth and I'm on Mars, and if you're trying to talk to each other, there is a 15-minute delay one way. You will say hi. So there's a silence of 15 minutes. Then I will hear hi. Then I'll say hi, again 15 minutes silence. So the hi will go 15 minutes, and I said hi, it'll come back 15 minutes. You'll get a reply after 30 minutes. So every time we speak, there's a delay of 30 minutes between us. Yeah, this is the problem actually. Now imagine these people, right? They send rovers and satellites or whatever to planets, and they control that satellites with a delay of half an hour and 1 hour. So unlike movies, maybe they show, right? Asteroid is coming, the hero is fighting there. People on Earth are sending signals and sending support. By the time people on Earth send support, that guy is gone. Everything got crashed. Nothing remains there. So what happens if the sun suddenly vanishes? We will not know anything. We will not see any difference of 500 seconds. So if this was the sun and this was the earth, so the gravitation we are receiving is not right now. So this gravitation field will start. So we are receiving the field due to the sun 500 seconds before. So T0, this is the time when the sun vanishes. So the gravitation field is still traveling even though the sun vanished. At this point here, roughly around T is equal to 498 seconds or something. So light takes 500 seconds to reach Earth. Light and field, dono. At this point, suddenly the sun goes dark, and then this guy then flies off tangentially. So for 500 seconds, you'll still continue in the orbit. Clear, everyone? Yeah, this is some of the field lines. Then, any doubt so far? Next thing. So all great properties and everything, but frankly speaking, what is exactly field? So we have created this theory saying, you'll interact and everything, great, but if you have to actually use in a problem, what is this exactly? So electric field, we represent with symbol E bar. It's a straightforward definition. It is a net electric force per unit charge. At a point. So the field at a point is the net electric force per unit charge at that point. Meaning, if you have a charge Q here at a point P here, if you bring a small charge to this point, the distance is R. So the force between them will be K, Q, small q by R square. And here we'll make sure Q is almost negligible, tending to 0, because we don't want this Q to come and interfere with the field of capital Q. Because if you bring one more charge in the region, that is going to mess up the field in the region. So we are trying to study the field due to capital Q so that it does not field of plus Q. So from the definition of the field is nothing but force by force per unit charge. So if you divide this, you'll get KQ by R square. Direction is R cap. There. This is the mathematical formula for field, KQ by R square. So field due to point charge. R cap is a unit vector. From charge to the point P. Great, we got the formula, but still not clear exactly why the hell we had to define this. I'll tell you why I had to define this. See, listen to this thing. Let me give an analogy. The problem, right, scientists have whenever we study something, right, they always like to study everything per unit. For example, think about this. When you're studying about a material, which is more intrinsic, mass of the material or density of the material? If I'm studying about iron, is it preferable to study mass of the iron or density of iron? If I take 1 kg iron, 10 kg iron, 1000 kg of iron, what is the density for all of them? Same, right? So it is mass per unit volume. So the same way, think of like this. Imagine I'm selling apples. So I buy an apple for 90 rupees and I sell the apples for one apple for 100 rupees. Again, listening, I buy an apple for 90, I sell the apple for 100. If I sell two apples, what is the profit? 20. If I sell 15, 150. If I sell 23, sir, you will say, sir, wait. What the hell are you doing? What kind of stupid calculation is this? You will simply say, sir, per apple, the profit is 10 rupees. Agreed? Multiply into number of apples you're selling. You get the point? Why should I take every time, 23 apples into 100 minus 23 apples into 90 and then do the calculation and then get the profit? You get the point? Even when I asked you what is the profit, you did the same thing, isn't it? You subtracted 100 minus 90, you got 10, and then you multiplied into 23. So the thing is, just like that, every time who will calculate that? So what we defined is at this particular point, the field is 10 Newton per coulomb, meaning if you bring 1 coulomb charge, the force will be 10 Newton. If you bring 20 coulombs, then it will be 10 into 20. If you bring 1000 Newtons into 1000. You're getting what you're doing? So technically speaking, field and force का बीच में कुछ difference नहीं है. Field and force are exactly the same thing. The only difference is field is per unit charge. That is, you're trying to find the force on a 1 coulomb charge. Is that making sense? So whenever you think about field, this is important, because see, when you're solving problems, when you're studying it, suddenly you get confused, like, here, what is field exactly? What is force exactly? Understand, both are one and the same. Force and field, there is no difference. If you find the force on 1 coulomb charge, it is called field. Is that making sense? The thing is, people love to study everything per unit charge. So per unit charge, the force is kq by small r square. If you bring some charge q2, then multiply into q2, you'll get the force. Clear with that? Right, Vihan, that is right. Why तो क्या इसमें mg by m? Is this making sense, everyone? So that is the meaning of field. It is a force per unit charge. So the force is given by charge into field. If q is positive, then the force will be in the direction of field. If q is negative, force will be opposite to the field. There, that is the only formula we have, k q by r square. Any doubts on this page? Next thing. What if you have multiple charges? So at this point B, if you have charge q1, if you have charge q2, and if you have charge qn, so this guy will give field E1 bar, this will give E2 bar, this will be En bar. So the field at point P will be the vector sum of all these fields. E1 bar plus E2 bar plus so on till En bar. Now, if you try to draw the field lines, if you put a plus Q charge and a minus Q charge, and if you ask to draw the field lines, so you know how they draw the field lines actually? They'll take a very small charge, they'll keep it here. They'll see which way it is going. If it goes this way, they'll draw a line, stop it. then put here, it'll go this way, then draw a line, put the small charge. So you make it move very small distances, like maybe in millimeters or something, and then you draw one line like this. Pretty cumbersome process, but you can get a rough feel. So charge lines will come from plus q, they will end at minus q. So you will get some lines from here also. Something of this sort. This is how it would look. What if you have both positive, plus q and plus q? So the lines will get pushed off like this. And like I said, the more lines you draw, the better picture you get. So the center will be a null point. Null point, or the field is zero in the center. That's how the field lines would look. So let me show you something. Look at this thing. So this is that, Colorado website. I showed you a few times there. So the entire screen is blank. So I can put some charges here. Say if I take a plus charge and put it here, can you see how the field lines came? So the brighter the line, stronger the field. Getting it? As you can see, as the lines are going away, they're fading away. So the magnitude is decreasing. So that is how they're represented here. If I put one more charge here, see if I add one more, can you see lines have become more bright? If I put one more, they're more bright. If I put one more, there's more bright. I can also add a negative charge here. See, the field lines will start getting converged there. I can add here. I can add here. I can remove this. So yeah, you can do a lot of things. See, the moment I put a negative line, the lines get pushed towards that negative. I can keep playing like this. So you can change the whole field in the region like this. This is a sensor. If I take this sensor and put it somewhere here, so it will show you the direction of the field at that point. And see, if you get very close, can you see this is a null point? There is no vector. And if you get very close to the charge, kq by r square, r will be zero, the field becomes infinity. So if you get close to the charge, you get an infinite line. Same thing, if you put it here, you get an infinite line. If you put something here, you can see the direction, the vector, how it is moving around. So you can play around with this. You'll get the idea about a field. So that's a bit about field lines. It's a computer generated. I'll send you the link. You can check it out. Yeah, I know most people play PUBG. Next thing. Clear with the idea here, everyone? There. So I taught you only one formula, kq by r square, which is actually same as the previous last class what we did. Bus wo k q1 q2 by r square mein q2 ko we made it as 1. Is that making sense? So anytime you think about field and force, think about that only. Both are one and the same. Instead of finding a force on q2 charge, you're finding a force on 1 coulomb charge. So let's see a question. So we have a 4q charge and we have a minus q charge. Both are fixed. And the distance between them is d. Find the null point. So find the point where the field is 0. Or in terms of force, if I put a charge there, it should not move. So where should a charge q must be placed so that it experiences 0 force? It's the same question. When you say null point, meaning at that point, if you put a charge, it won't move. I hope everyone is convinced with that part, right? Field and force are same. Field is simply force on a 1 coulomb charge. I think if you understood that one point, it'll be very easy for you to understand. Questions are easy to solve. No, it's not 2D by 3. Let me ask you a question. Say, we have a problem here. If you take a point in the middle, what is 4q ka direction? 4q will push, isn't it? It will push to the right. What will the minus do? Minus also will pull. They're not cancelling, right? अब सोचो ना logically, if you put a plus q charge here, 4q will repel and minus q will attract. Why will the force cancel? Are you getting it? So null point cannot be in between the charges. This is not plus 4q and plus q. Is that making sense? So the null point is not in the middle. So the thing is, you have to ask yourself. So we have three options here. Let's say we have a point A here, we have a point B here, and we have a point C here. B cannot be the null point. You're getting it? Because at point B, the field adds up. So if I try to put some color here, I'll do one thing. Wait, I'll change this into plus red color. I'll change this to minus color, green color. So we're talking point A here, point B here, and point C here. Now look at this. At point B, 4q is pushing to the right. At point C, 4q is pushing to the right. At point A, 4q is pushing to the left. The negative charge at point B is pushing this way, and here it is pulling this way, and here it is pulling this way. Is this making sense? And you can clearly see at point B, they can't cancel. They're adding up in the same direction. At B, fields add up. At point A, there is a problem. Can you tell me why point A also can't be the answer? I agree. At point A, both are opposite. But look at the problem here. The 4q ka charge ka magnitude is more, and now you're keeping distance also small. Your charge ka magnitude is already more. You're stronger. On top of it, if I keep you closer, you'll become even more stronger. So can ever the fields get cancelled? They can't cancel, right? See, in order to cancel, the directions must be opposite and the magnitudes must be equal. So at point A, the field due to the 4q will be greater than field due to q. So at these 2 points, you can't have a null point. That is the first thing you need to realize. You cannot have a null point in the middle, and you can't have a null point closer to the 4q charge. Then the only option you have left is C. Because at point C, 4q is far, distance is also far, so it works out that ratio. There is a chance. So let's draw the picture again. So we have 4q and we have minus q, and let's say this point is your null point on the right hand side. Let this distance be x. This distance is d. So 4q is pushing with a field of k, 4q. So at the null point, we will have The 4q is pushing with k. 4q by d plus x whole square. This minus q is pulling inwards, which is k, q by x square. So it's pulling this way and that is pushing away. Getting it? I'm showing it on a picture, so I'll not put minus there. I'm just taking the magnitude and then you're done. So if I equate these two, 4k cube by d plus x whole square is equal to k cube by x square. Kq will cancel. You'll end up with d is equal to x, or x is equal to d. Is that making sense, everyone? You have a null point on the right hand side, not in the middle. Clear? Let's see one more. You have a regular hexagon side A. This is plus q, minus 2q, plus 3q, minus 4q, plus 5q, minus 6q. Find the field at the center. Both the magnitude and the direction. Zero or null field. It's not zero. Zero कैसा आया God? See. So for convenience, what will I do? I will write E is equal to k q by a square. So look at this. So this plus is positive, so it will push with E. Minus 2q is negative, so it will pull with 2e. So 1q charge will give E ka field. 3q will push with 3e. Minus 4q will pull itself towards 4e. 5q will push with 5e. You can see the direction, the vector is becoming bigger. This guy will push with 6e. Isn't that how it looks? Now if you add all the points here, you can clearly see Class, I gave you a problem like this. This is 5e, this is 7e, and this is 9e. And the angles between them are 60 and 60 here. Make sense? So you're done. So the field at the center will be, that will be 7e cos 60 plus 5e cos 60 minus 9e I cap, horizontal components. Vertical direction, 7e sin 60 minus 5e sin 60 j cap. So solve this. How much will this be? Minus 3e I cap plus root 3e j cap. That's your answer, where e ka value is k cube r square. Clear? Any doubts on this? Next thing. Next one. And this is important, right? We are going to see this again, in gravitation, they can also ask in magnetic field. So listen carefully. I'll show you one and then I'll ask you more on this. Basically, I have to draw a graph. So let's say we have two charges, plus q at minus d comma 0. We have plus q at d comma 0. So now you're walking on the x-axis. So as you're walking on the x-axis from left to right, you will experience some electric field. So we define Ex. Ex is a electric field on the x-axis. And the sign convention, if Ex is along I cap, we take it as positive. If Ex is along positive x-axis, we treat it as positive. So if you stand somewhere here and if you get the field is 10 I cap, then you'll draw it as plus 10 in the graph. Plot Ex versus X graph. So if a person is going on the x-axis from minus to plus infinity, how will the graph look like? So I'm asking you to draw this graph. So here this it will be not y coordinate, it will become Ex versus X coordinate. You're getting the meaning of it? You need to plot a graph Ex versus X. Right side is positive, left side is negative. Think for a minute, give it a try, whatever you think. Then I'll show you one, then I'll ask you more. Because the directions and all could be a little confusing. But first you try on your own for a minute, whatever you think. But quite a good important question because it can be asked in 3 different chapters. Or there's a null point. It won't be a parabola. Let me help you with this one. Next one you can try. See, first let's be very clear. I'll do one thing. I'll change the color here for understanding. So when I draw green line, meaning the right side charge is dominating. When I draw red line, the left charge is dominating. Great. So first thing, if you get very close to a charge, what happens? Let's start from there. KQ by R square. If you make R very, very small, the field will become very, very large. It becomes infinite. So if you're near this right side, the green charge, the field will be away from this side and away from this side. That means if you're a person standing here, you will think field is going to the right side, isn't it? If you're a person standing on the left side here, you will think the field is going left side. Is that making sense? So direction will change. The moment you cross the charge, direction will change. So the green one ka directions are like this. The red one ka directions are like this. Great. Now, first let's try to get the values and then we'll go to the graph ka part. So let's say you're standing at infinity, minus infinity. What is the value you will see? 0. Agreed. Let's say you come closer here. So what is the direction of the field here? The field is left side and you're standing here. You will see some value, let's say minus 5. You're getting it? Let's say you stand here, what will you see? Minus 20. Let's say if you stand here, what will you see? You're going to the left, so minus 100. If you stand very close to this, what you will see? Minus infinity. So इसका graph कैसा plot करेंगे? 0, minus 5, minus 20, minus 100 infinity. The graph will look like this, isn't it? Are you getting how to draw the graph? What I'm asking you? As you get closer and closer to the value, ex ka value will become minus infinity. Are you sure, everyone, what I'm drawing there? Now, if I go and stand here, what will be the value? Plus infinity. Suddenly the direction has changed to the right side. Magnitude is still infinity, but the direction is right. If I stand here, then it will be some plus 10. If I stand here, I'll see null point because both the fields will cancel. Once you cross this, now this guy will experience, see, the right side charge will dominate because you're closer to that. You're pushing to the left, minus 10. If you get too close, you'll get minus infinity. If you cross this, you'll get plus infinity. You cross this, plus 100. You cross this, plus 10. You cross this, 0. Are the numbers making sense? Now I'm asking you to draw these numbers on a graph. Sure. Getting it right positive, left negative. So if I try to put this on a graph, this is how the graph looks. The graph will start at 0, will get closer to this line. Then it starts at infinity. At the center, you'll get a null point. Once you cross this origin, the green will start dominating. And then once you cross this, field will be pulled to the right. This is how it looks. No, wait. It's the plus Q, right? Is this clear, everyone? Now, one thing I'll tell you, drawing the graphs is difficult, but in the exam, it is easy to eliminate the graphs. So there are few signs you can clearly see. When you get close to the charges, the value should be infinity. Find the null point. That's the second data point. At infinities, you should have 0. If you know this much now, you'll be able to eliminate graphs. Is this graph understood, everyone? So basically, you'll get this person will see all these values and you're putting them on a paper. Are you clear what we are drawing? Any doubts on this? Clear, na? Parth, Puruja, Surya, Vihan, clear. Niharika, clear. Ojas, Ishana, Kavya, clear with this. So using this as a logic, can you draw this graph now? Similar question, but this time Let's say this is minus q, this is plus q, minus d comma 0 and d comma 0. Let's get this. I showed you plus and plus. I'm asking you plus and minus. This is not even the actual question. Next question, C is the actual question. But give it a try. Slow. That slowly will bump up your graph drawing ability. Done. Now verify your answer. Remember, this plus q will push the field away from the charge. This minus q will pull field towards the charge. So when you're at infinity, you get 0. It looks like this. Now here, there is no null point. Remember, in this thing graph, there is no null point here anywhere. There will be no null point in the system, and the plus will start dominating. It will pull towards. This is how the graph looks. There are no null points on the system. Is this clear, everyone? So wherever I draw the graph with the red one, meaning the red charge is dominating, uska field is more stronger than the green one. So at this point here, you get a minimum field, but that is not null point. Is that clear, everyone? Any doubts on this part? The left-hand side, the middle, right-hand side, anything you didn't get, please ask. If you're standing here, you will think plus infinity. If you're standing here, you'll feel this is also plus infinity. So the graphs are two plus infinities there on either side. So definitely graph has to come down and then go up again. That much we can say. Sure, everyone? Let's see one more like this. I think if you got this one, then yeah, you would be able to handle most of the graphs. But like I said, eliminating graphs is more easy. Let's say this is 4q, which is at minus d by 2 comma 0. This is minus q, which is plus d by 2 comma 0. This is the first question we did today. ये question था ना, find the null point. Draw the graph for this. 4q minus q. This would be even an advanced question. Try. I'll give you 2 minutes. It's a worthy question. Ready? So if I have to solve this in the exam, what will I do? First of all, say I'll not try to draw. I will try to see some key points here. First thing, मुझे इतना पता था, graph should be 0 here, infinitesimal it will be 0. Now look at here, if you get too close to this, at this point it should be plus infinity. So graph it should be here like this, starting from the top. And here on the right hand side, graph is no wait, I wrote reverse. Graph will be minus infinity starting from the bottom. Here graph will be like this. You're getting it? So near the charges, magnitudes are infinities. Similarly, minus q, it is pushing this way. So this graph also must be like this. And plus q is this way, like this. And I already calculated null point will be somewhere here. So the graph must cross this line somewhere here. You're getting this? This much data points I have. Now check in the graphs which are working with these data points. And you'll be able to eliminate at least 3 graphs eliminate ho jayegi. You'll get the answer. Getting it? So this is what I was saying. Solving a graph actually is easy to eliminate. Now let's try to draw it. So you're at infinity or 0, and as you get closer to this thing, 4q is pushing down. So this guy will look like this. Great. Now from here, it will be like this. The minimum will occur somewhere here. I don't know where, but definitely not in the center because 4q is so strong, it will push the field. It will dominate till here. And then the graph will turn up. So it will be a little unsymmetric. It will not be so symmetric like the previous one. Now, where is that point? We can do mathematically, but I know it will be towards the more to the right side. Now, this is where interesting thing happens. This graph will start from here. It will cross somewhere here. This is the null point. Now, let me ask you this. What is the field at null point? 0. What is the field at infinity? 0. So this graph which is going up has to go up and then come down. Na? Think about it. If it is initially 0, finally 0, ये graph तो possible नहीं है. It can't be a horizontal line like this. Right? This is also not possible like this. Why? If it goes like this, can you see a sharp point here? Graph is not continuous. You can't have a discontinuous graph like suddenly out of nowhere. So there is a better argument. Think about it. If you stand very far, this distance becomes negligible. Then what will you think the whole charge is? You will think this total charge is plus 3q, isn't it? So for a person who's standing very far, usko lagega, he is looking at a plus 3q charge. So the positive charge will dominate when you're very far. So the graph will look like this. So the green will dominate here. Now suddenly the red will start dominating. It will increase and then decrease to 0. You're getting the graph. So on the right hand side, the red will again come back into the picture for some time. So, and the argument is this. So when you're very far, if we take a point very far, it looks like a plus 3q charge. Is that making sense, everyone? So then this question, this right side part is the more tricky one. I know this is 0. I know this is 0. The graph suddenly can't become 0. So it has to go up and then bump down. Something like this. Clear, everyone? It's a pretty good one. Please ask me if you're confused here. You can't actually draw these graphs in gravitation manner. You have all negative charges only, right? Gravitation where there's no positive. So graphs in gravitation are actually easy. In graphs in gravitation will look like minus q because it's always attractive. There is no repulsion in gravitation. That's what I keep saying. Electrostatics is a much superior chapter than gravitation. If you can do electro, gravity will be done very easily. Clear with this? Take a break. Come back by 7:3. We'll continue from here. Any doubts so far? Right. Come back in 10 minutes. Yeah, comes on everyone. Let's see one more. So this is x is equal to 0. Particle is projected with u and theta. So this thing ka charge is plus q and the mass is e. Gravity is there. On top of it, you also have a field E, which is equal to E naught into T. E naught is constant and T is time. So someone switched on an electric field at T is equal to 0, which is increasing with time. So you're getting it. So as this guy is flying, there are two forces acting on it, isn't it? Mg, and also you have E into Q. So there's a horizontal force also pushing it forward. Find the time of flight, find the maximum height, and find range. Find H max, find time of flight, and find range. Yeah, right, Puraja. How do you approach this, Surya? Right, people figure out this thing. The time of flight and H max will remain same. That is the first thing you need to figure it out. Because H max and time of flight will depend only on the vertical forces and vertical velocities. So nothing is changing in the vertical direction. The system doesn't care. The H max and time of flight will remain same. What messes up is the range. Let's see. So if you look at H max will be u vertical square by 2a vertical, that is u square sine square theta by 2g. Time of flight will be 2u vertical by a vertical, which is 2u sine theta by g. So this thing will not get affected, right? Vertical components are unaffected by horizontal acceleration. Clear? Then let's say as this thing is flying at some time t, right? We will have two accelerations now here. So the ax will be how much? So the horizontal force Fx will be E into Q is equal to mass into horizontal acceleration. So this will be E naught into T is equal to mass, and this can be written as dVx by dt. Acceleration is not constant, so you can't use S is equal to ut plus half at square. So from here we will get dVx is equal to E naught by m t dt. Integrate this. So initial velocity u cos theta, this will be some Vx, this will be from 0 to time. So we will get Vx minus u cos theta, so it will go the other side. You will get u cos theta plus E naught t square by q भी आएगा एक by 2m. Then again integrate this, Vx is dx by dt, u cos theta plus q E naught by 2m t square. So we will get dx. You want to find range, right? So this will go from 0 to r, that is a range. This will be u cos theta dt. Time will go from 0 to time of flight plus q E naught by 2m integral t square dt 0 to time of flight. You're done. So there you will get range is equal to u cos theta time of flight plus q E naught 6m time of flight cube. Substitute the values, you'll get the answer. Is that clear, everyone? You have to integrate it in the horizontal direction since the acceleration is not constant. All clear with this? Any doubt on this? That way. Next one. Anyone not clear with any particular step? Clear, na, Daksha? Ahana? Clear? Arush? Clear? Arya? Arnav? Next one. We have a pendulum here, mass m, charge q, length L. Gravity is there. At t0, suddenly an electric field is switched on. If you suddenly switch it on, what will happen? This will start swinging. Find the maximum angle deflected. If the pendulum is held at rest at equilibrium So that's the first question. Second question, if the pendulum, so you brought it to equilibrium, is placed in equilibrium position at rest, then find time period for small oscillations. Yeah, that is wrong. What is the first one? Get the first one. नहीं है ना? See, horizontally यहाँ पे क्या होगा? This is tension, this is mg, this is eq ना? The forces are not balanced. This will start moving. Vertical position is not equilibrium. What is the first part? Let's see. Now, the most common mistake now, what people do, they think the point where the force is zero, it will stop. That is a mistake there. You need to understand the point where the forces are zero is a mean position. You don't stop at mean position. You have maximum speed there. So basically, initially you're starting with zero velocity. This will be zero velocity. This is your mean position. And at this point, the body has maximum speed. Understand this thing. Initially, EQ ka component is greater than mg. So speed will keep on increasing. Once you cross the mean position, mg component will be greater than EQ. So you'll decelerate. So you can actually guess the answer pretty easily from here. This is your theta mean. So at this point, if you look at the forces, this is EQ, this is mg, that is your theta mean. So tan theta mean will be EQ by mg. So this also will be theta mean by symmetry because both are extreme positions and this is the mean position. So the maximum angle deflected theta max will be 2 times theta mean, which is 2 times tan inverse EQ by mg. Done. This is the easiest way to solve. But let's say you click nahi hua and you want to solve this. Then we have to use work energy theorem. This is theta max. So this horizontal distance will be L sine theta. This vertical height will be L into 1 minus cos theta. And you're having EQ here. So work done by external forces is change in potential energy plus change in kinetic energy. Here external force is EQ. EQ into L sine theta, force into displacement. Change in potential energy is mgl into 1 minus cos theta. Kinetic energy is 0. You solve this, you can write sine theta as 2 sine theta by 2 cos theta by 2. You will get tan theta by 2 is equal to EQ by mg. You will get theta is equal to 2 times tan inverse. We have to use conservation of energy. You can't use forces. This is an alternate way.
Sir.
Yeah.
Sir, could you explain once again why 2 theta max is 2 theta mu?
Seriously? You did so much SHM and you're asking now.
Right, using work power and a method I got
I
it, but like
forgot. That is okay. You tell me now. From extreme position to mean position, if you have some distance, what is the distance from mean to the other extreme? Ah, God. Symmetry, right? If this is an extreme,
okay. Yeah,
this is an extreme, and the mean is in the middle. So yeah, they should be equal then.
okay, so
You're getting it now. This becomes down now.
yes.
Is that clear, everyone? And at this position here, what is the gravity? So if you draw the diagram at the mean position, this is your mean position. If you keep it in equilibrium, this will be tension, this will be EQ, and this will be mg. So system will think this is down. And what is G effective? So tension will be root over mg square plus EQ square. That will be equal to m into G effective. So we have G effective is root over G square plus EQ by m whole square. Therefore, time period will be 2 pi root over L by G effective. Check. That's your answer. Making sense? And this thing, it looks like which question? ये question याद है? Second one? Isn't it the same question? सिर्फ MA का place में EQ था. The lift going horizontally. Able to see the resemblance? So G effector still works. So if you see G effector you have seen in fluid mechanics, SHM, you will see here. So the equation doesn't care whether it is G or G effector, you'll get the answer. Is this clear, everyone? Clear, na, Vihan? Next one. We got a solid hemisphere, a solid sphere. Mass m and radius r. The entire upper region is positively charged. The entire lower hemisphere is negatively charged. The ground is rough and there is no slipping. Then what you did at t is equal to 0, suddenly you switched on a field E. अभी देखो क्या होगा. When you switch on the field, all the positive charges will get pushed to the right. All the negative charges will get pushed to the left. So this thing will start rotating, isn't it? The upper hemisphere is pushed to the right and the lower hemisphere is pushed to the left. Find angular acceleration and omega as function of theta. What will be the angular velocity of this sphere after time t? Or as function of theta? So upper hemisphere is uniformly charged and lower hemisphere uniformly charged with plus q and minus q. At t is equal to 0, a horizontal electric field is switched on. So this thing will start rotating. Meaning if you look at the picture, it will look like this. So initially sphere was like this. Now the sphere would become like this. So अगर ये ऊपर वाला positive, negative. So the sphere must have rotated an angle theta. Find the angular acceleration alpha and find omega as function of theta. How do we do this? Anyone didn't get the diagram, please ask me. As function of theta पूछा रहा है अंश. तेरा आंसर में थीटा है ही नहीं. बट 8 आया क्या? 8 नहीं आएगा. 28 आएगा. See, where is went wrong? Think for a minute. I'll tell you how do we even start actually, because it looks so weird, force and also. So there is a thing we need to use. Let's see. Logic to वही अंश. Now see, suppose if I take a hemisphere, now when there is a gravity here, tell me one thing, when you have gravity, does mg act at only one point? We know the gravity acts at every point dmg, 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 and dmg, and so on. But then we proved in center of mass chapter, instead of taking mass at every point, you can replace all this at one single point, center of mass, and then we can say this is mg acting here, and then we can solve the problem. Isn't that what we did? Does gravity act only at one point? No, right? Gravity is uniformly distributed everywhere, but we can problem solving, it works out. So we choose mg at center of mass while drawing an FBD. And then from there we calculated torque, force, everything you could do. So the way it works out. Whereas in reality, the weight is not at a single point, it is actually distributed. Using this logic, like I keep saying, as long as the equations look same, Max doesn't care what you're talking about. So when you switch on the field E here, so this point will have dq into E. So small charge into field, dq into E, dq into E, dq into E. So dq का place में we had dm and E का place में we have g. So what will the system think? the system will say, okay, from that logic, I can also say all the charge is located at center of mass, and it will experience a force of EQ. Is that making sense? So you can just replace the whole hemisphere with a 1 point charge at the center of mass and then start solving the problem. Now it becomes easy to handle it. So we can see by symmetry, the EQ acts at the center of mass. Getting it? So some people like to call it center of charge, but remember, technically it's a concept hai nahi. But if it is easy for you to remember that way. But remember, there's no concept called center of charge. The only headache with this thing is headache nahi hai exactly. Matlab, you know only center of mass for uniform distributions, isn't it? So we prefer to use this for uniform charge distributions. If the charge distribution is non-uniform, then you have to find the center of mass of the non-uniform and then get it. So that's a headache. Valid for non-uniform field, that is better. If the field is variable, then you can't do this. So now how will the question look like? So let's say the sphere is rotated by theta. So this all upper charge can be located here, plus Q. So this will experience a force EQ. This distance is 3r by 8. This will be minus Q. This will be EQ backward. This will also be 3r by 8. This will be the friction. This is alpha. And this is the acceleration of center of mass. Now get it. Hope everyone remembers the center of mass of hemisphere. If you forgot center of mass is gone, rotational mechanics from moment of inertia is gone, right? Fluid mechanics is gone. Literally center of mass keeps swapping everywhere. Now solve. There, I did everything. It is done. Now it is only max. So the main part of the question is figuring out that you can replace the whole charge at the center of mass. And once you got that, your job's done. What? You thought center of mass will leave you alone? Mechanics will keep haunting you. Nothing is going to leave you. Even though the whole thing we call electromagnetism, from beginning till now, you saw half of the questions are mechanics only, isn't it? And this is a pretty good one. If you see electrostatics, center of mass, rotational mechanics, they have 3 chapters. Omega in terms of theta, everything in terms of theta. Don't bring time, because time calculate nahi kar payenge. This is not an SHM. It gets really messy. Meaning you will get a form like d theta by root sine theta root cos theta, ऐसा कुछ आएगा integration नहीं कर पाएंगे. So if it is not slipping, what is the best point to take torque? Our favorite point is the bottommost point, since it is not slipping. And next thing, if you notice one more thing here, EQ is actually a couple. 2 equal and opposite forces. And torque for a couple is independent of axis of rotation. If you guys remember that. If you take a couple, torque about any axis is same. So torque about point A will be EQ into perpendicular distance between the 2 EQs. That will be 3r by 8 cos theta into twice. This is equal to IA into alpha. This will be 3 EQ R by 4 cos theta. Torque about A will be 7 by 5 mr square alpha. This is 15 EQ cos theta by 28 mr. Sorry. Then alpha can be written as omega d omega by d theta. Integrated on both sides. Left hand side will become omega square by 2. This will become 15 EQ by 28 mr sin theta. There, omega आ गया. Clear? I assume theta with the vertical. दिया ना पिक्चर में. See, angle rotated, right? So you can take any line and I took it that way. Other steps clear, everyone. Calculations are not tough, na? Dekha? Meaning it's just simple one equation, you'll get it from the whole thing is to figure out that you have to use center of mass. Is this clear, everyone? I could have taken a disk also. Discus center of mass. What is a discus center of mass? Half disk. Half disk ka center of mass. Kajnis. 4r by 3 pi. Right. Half ring ka? 2r by pi. Bhulna mat. Clear with this? Now, if I actually ask you how is the motion looking, can you tell me how will the motion be? Will the sphere just keep rolling forever? This will be plus. This will be plus. This will be plus. This will be plus, and this will be plus. Minus, minus. So now see, if you look at the forces, this will be EQ, this will be EQ. Initially, angular velocity is 0. Angular acceleration is maximum. Then this is EQ, this is EQ. Alpha and omega both are in the same direction. At this point EQ and at this point EQ. Can you see both are in the same line? They'll cancel. Alpha becomes 0 and angular velocity omega is maximum. This is a mean position. So when it rotates 90 degrees, torque becomes maximum. Angular velocity becomes maximum. This is your mean position and we have maximum omega. Now once you go here, this would be EQ and this would be EQ. Now alpha will act backward and omega will act forward. It will start decelerating. It slows down. And then finally, this is EQ and this is EQ. Omega becomes 0 and again you'll get a maximum alpha on the other side. So the motion, right, will look like this. If you're looking at my screen, it goes front, then comes back. It goes front and comes back. It will do half revolution, 180 degrees. So at this point, theta was 0. Here at this point, theta is 90 and theta is 180. This is an oscillatory motion. Is this making sense, everyone? So the sphere will keep going. After 90 degrees, torque becomes 0. Now you'll slow down. Then you stop at 180 degrees and then you'll turn back. Clear with this? The sphere will not keep going in one direction. It's a good one. Any doubts on this? That is how the motion will be. Clear with this, everyone? Next thing. So that is a bit about a field. And if you see, we only dealt with field things. Next thing is electric potential energy. If there is a force, there is always an energy. electric potential energy and electric potential. Now we'll not get into the derivation and everything. We'll just put on the main result. So if you have two charges, Q1 and Q2, and if the distance between them is R, the potential energy of this system, right, is given by U of R. So that is a potential energy as function of R. That is the meaning of this. Where R is the distance between the charges. So we have U of R minus U of infinity is given by K, Q1, Q2 by R. You won't get R square in the denominator. Sorry, R. Remember potential, you'll always get potential energy difference. You're getting it? So if we take infinity as reference, if infinity is taken as a reference, then you will take U of infinity as 0. Then your formula becomes the potential energy is equal to K Q1 Q2 by R. So reference is infinity. There. This is the main result you need to remember. This is also an important one. Because exam is sometimes they'll ask you like this. If U of infinity is not 0, but let's say it is 100 joules. And let's say this is Q, and let's say this is minus 2Q, and let's say this is R. Then they'll ask you find the energy of the system. Then the energy of the system will be minus K Q K Q minus 2Q by R. So U will be minus 2KQ square by R plus 100. It's basically shifting of origin. So that is the main formula there. You can remember that KQ1 Q2 by R. You can put on this thing here in the red box. How did we get this? Now, if you want to derive this, we can do that. If you remember, it comes from work per energy, work done by internal conservative forces. Is equal to minus delta U. So work done by internal conservative forces will be K Q1 Q2 by R square into dr is minus delta U. The reference will go from R to infinity. So from there you can solve and you can get it. That is a force, right? Force into displacement. Force is changing with distance R, and from there you will get it. So that is one. Great. Now if you look at the formula here, K Q1 Q2 by R, you have to take with signs. So we can get even negative energy. What does even negative energy mean? What does negative energy mean? So energy is one thing, a very peculiar thing. You can actually compare energy with money, and it looks. You can compare between R1 R2 also are here. Then you'll get potential energy from R1 to R2.
Yes.
But you'll get difference, na? That way. So think of like this. Let's say if you are in debt, if you owe me 1 lakh rupees, what is the meaning of that? How much money do you have? You have minus 1 lakh. What is the meaning of that? Until and unless you give me that 1 lakh money, I'm not going to leave you. Isn't that the meaning of it? If you are in debt, the person is not going to leave you. So negative energy systems, right? They indicate system is bounded. Meaning in order to separate the system, you need to provide this much energy and then the system will get separated. These are called bounded systems. Basically, these are the systems which are stable. For example, if I kick you with a speed of 11.2 kilometers per second, you will leave the earth. That is the escape velocity. Meaning we have this much energy, negative energy there, and if you give that much, you'll go off. And this is not the first time you heard this term. Huh? You heard this in chemistry. Anyone remembers? What is the energy of an electron in the first orbit? Minus 13.6 eV. What is that minus meaning? If I give 13.6 eV, the electron can be separated from the nucleus, isn't it? You can send it from first orbit to infinity. So the electron is bounded. You also call it as binding energy, if you remember that word. So that is the energy which is binding the system together. So negative energy is not really that new. You have actually heard about it. So energy of an electron in first orbit of hydrogen atom is minus 13.6 CV. So what it means is that is we need to provide plus 13.6 CV. It is in depth to separate the electron from the nucleus. So when it goes to infinity, energy becomes zero, means you got separated. Similarly, positive energy systems are repulsive. If a system has a positive energy and if you leave them, automatically they'll repel and fly off. So these systems are not stable. They don't exist in nature. Yeah, you can keep them forcefully, but if you give them a chance, they will always fly off. They're not stable systems. And what if you have multiple charges? So you can write one more statement here. You can also write potential energy can be also defined as the amount of energy required to assemble a system. So if you want to create a system, and if you bring one charge from infinity, all the work that you did must be the potential energy of the system. Whatever effort you keep, in order to create that system must be the energy stored in the system. Assemble a system by bringing individual charges from infinity is potential energy of the system. Meaning, what do you mean by that? See, for example, if I keep plus Q1 charge, is there any energy? You just have one charge there. Is there any energy? Nothing. Now, if you bring a Q2 charge, forcefully, if you try to bring it closer, will this guy keep quiet? It will fight back, right? So I have to push against it. I pushed it, I pushed it, I pushed it, I pushed it, and I kept it here. Abhi yahan se yahan tak, to bring it, whatever work I did must have gone somewhere. And what is work done by external forces? Change in potential energy plus change in kinetic energy. Initially velocity zero, finally velocity zero. So all my work must have gone into potential energy. Make sense? There. So that is the meaning of that statement there. Clear with this? Then what if you have multiple charges? Let's say we have Q1, we have Q2, we have Q3. Then the potential energy of the system will be the potential energy of all possible pairs. So that is U12, U23, and U31. So that is, so you take every possible pair that is there and find the potential energies and add them up. It's a scalar quantity. So this is the energy of all possible pairs. So if there are 3 charges, we have 3C2. If you have 4 charges, then you have 4C2. If you have n charges, we have nC2. So out of n charges, you have to select 2 of them as a pair. Is that clear, Arya? There, that is the formula there for energy, kq1 q2 by r. Remember, force is kq1 q2 by r square. Field is kq by r square. Potential energy is kq1 q2 by r. Then we also have something called potential. We will see that later on. Let's see a question. We have an equator triangle. So we have a charge plus q on the vertex, plus q, plus Q, and plus Q on the centroid. So you have 4 charges there. Equilateral side A. Now someone took these 4 charges and they rearranged it into a square where this was plus Q, this was plus Q, and this was plus Q, and this was plus Q. This is also square side A. So when you're trying to do this, you have to put some work, right? They won't go on their own. Find the work done by external force to rearrange the system. So the charges are on an equilateral triangle, you rearrange them into a square of 4 charges on the vertices. How much work did you do to rearrange the charges? Let's get this simple one. We have some pretty good questions on energy, which we'll be handling in the next class. Next class will be quite important. We'll be doing an extensive integration, different shapes. So if you see today, all we did was point charges. And again, whatever I'm teaching you, everything is exactly same as gravitation. You just need to replace Q with M and you'll get all the answers. And here actually you get even better answers than gravitation. Again, what is work done by external force? Change in potential energy plus change in kinetic energy. Here, the kinetic energy is not there. So you just have to find the potential energy. So final potential energy minus initial potential energy. So how many pairs are there here? 4C2. There are 6 pairs. So you have to, there are 6 terms, and here there are 6 terms. Get them. I'll give you a minute more. Right, Rehan. Get something like that. All right. Right, Ishana. So how many pairs are there? Look at this thing. We have 3 side pairs and we have 3 centroid pairs, isn't it? 3 sides and 3 centroids. Here, 4 sides and 2 diagonals. You're getting the 6 pairs? So here, the initial potential energy will be K, Q, Q by A into 3. These are the side pairs. Plus K, Q, Q. Remember, from the vertex to centroid, the distance is A by root 3. It will divide in the ratio of 2:1. A by root 3 into 3. These are the pairs with the centroid. U final, K, Q, Q by A into 4. These are also side pairs. Plus K, Q, Q by root 2A. These are the diagonal pairs. There, total 6 and 6. Work done by external force is change in potential energy plus change in kinetic energy. Here system initially is at rest, finally at rest. So this is U final minus U initial. So if you subtract this, you will get KQ square by A common. The 4 minus 3 side pairs, that will cancel 1 plus root 2 minus 3 root 3. Check, that's your answer. All clear with this? Easy. So if you have multiple pairs, this is how you do. Any doubts on this? Clear, na everyone? Purja, got it? Confused?
Wouldn't it be negative of that?
U final ये है ना, this minus this, right?
But work done by external.
Internally है ना, external है ये.
Yes, sir. Yes.
Clear with this? So there. So that is the last one for the day. So next class when we catch up, we'll continue from here. We will do a few more problems on this. We have some pretty good problems based on kind of collisions kind of thing on energy part. And then we will do, potential and field for continuous bodies. That is quite an important thing. Whatever integrations we do, again, you will see some similarities to Centromaska integration. And the same integrations we can do in gravitation, we can do it in magnetic field. So yeah, I think next 2 sessions will be we'll have good amount of integration, good models. Okay, so that will wrap up for the day, right? SHM ka chapter got over last week, so please start solving, finish off whatever backlog you have. And this week there is an exam on SHM. Deadline is Sunday, so make sure to give it. So if you have any doubts in the class notes, you can stay back and ask. Any other doubts, you can stay back and ask, or else you're free to leave. So, Daksha, bolo na.